Hello everybody, my name is Konstantinos Syngros and I'm here with my colleague Alan Popel, and today we're going to talk about soil foundation superstructure interaction for tall buildings on combined pile-raft foundations. We are going to start with definitions. We're going to proceed with the process of foundation design for tall buildings and soil modeling for structural design. And then we will demonstrate the various modeling aspects in a case study and conclude with some final remarks. Definitions. Here we see a sketch of a tall tower on top of a raft foundation. Right there. And because tall towers are very heavy, they cause significant differential settlements at the foundation level, which can overstress the walls, and they can even cause noticeable movements at the tower top. A special study is needed to determine and limit those differential settlements, and this is kind of what we're going to be talking about today. This gives you a little taste of what's coming. To determine the differential settlements, the structural engineer uses springs under the tower to represent the soil, whereas the geotechnical engineer models the foundation and the soil. So today we will be talking about how the geotechnical and structural engineer work together to determine such springs to model the soil. Now, what is a raft foundation? It consists of a reinforced concrete slab that supports the columns and walls of a structure and distributes the loads to the underlying soils. The raft foundations are considered when individual footings cover more than about half of the building area, and when those footings cause total and differential settlements that are too high for the structure to take. On the right, we can see an example of a raft, also known as a mat, of a case study we're going to be seeing later, and the little dots represent various column locations and wall locations at the top of the raft. Now, in general, the piles are used as settlement reducers and are placed under strategic locations under the raft or under the whole raft. This diagram describes the concept behind the Pile-Rafts, where the foundation initially is, the load is taken initially by the piles and the raft elastically. Then as the load increases, the pile capacity is fully utilized, and at one point the raft contribution starts to increase, until finally both pile and raft capacities are reached, and then the foundation ultimate load is determined. These are some examples of Pile-Raft foundations of projects we have worked on. The two projects in the US, to the right, use piles under the raft in strategic locations to make the differential settlement smaller, whereas the two projects in Malaysia use piles under the entire area of the raft because the tower loads were too high to handle. So here we compare settlements of a raft and a raft with piles. On the left-hand side we have settlements of a raft alone, and we see that some differential settlements are high and the structure cannot take them. From 2.5 you go to 0.8. Whereas if you put piles under the center of the raft, you end up reducing the differential settlements, and therefore the angular distortion is reduced to half from the case where you had the raft only. Now we're going to talk a little bit about the process of the foundation design for towers. Typically, the project team involves the developer, the architect, the structural engineer, and the geotechnical engineer. But for major towers and big international projects, the team may collaborate with local consultants, peer reviewers, and finally specialty foundation contractors. Now, the steps to develop the foundation system typically start with a geotechnical site exploration, which involves typically in situ testing, laboratory testing, to develop the geotechnical parameters for the design. Then the structural engineer provides initial tower loads, and some initial studies are being carried out by the geotechnical engineer regarding the bearing capacity and the settlement of the foundation. These studies are then refined by an iterative process that happens between the structural and geotechnical engineer, and at one point the peer reviewers get involved, and then the design may change and may continue to evolve. Later on, there is the contractor selection process to be followed at the end by the local authorities approval process. So, to quickly get an idea of the iterative process between the structural engineer and the geotechnical engineer, the structural engineer provides the column loads to the geotechnical engineer, who has already developed a model of the foundation and the soil. And the geotechnical engineer evaluates the foundation settlements and stresses and provides the structural engineer with Winkler springs or soil springs. Then the structural engineer runs their model, and they determine the foundation settlements and stresses under the raft. They compare with the geotechnical engineer, and either they are close enough or the geotechnical engineer needs to revise the springs and come up with new foundation settlements and stresses. This process keeps happening until the settlements between the structural model and the geotechnical model are close enough to have a convergence. Now, in the case of combined pile rafts, in addition to the raft, you have the piles. So in addition to convergence in raft settlements, you will require to converge also on the pile loads, the pile subgrade load sharing, meaning how much of the total load the piles are going to handle and how much the soil underneath the raft is going to take. And then the structural engineer will check if all these springs cause the column wall loads to change. Now we're going to continue with the soil modeling for structural design. Structural engineers use springs to represent the soil, as we said. For a given foundation, for a given column load, the foundation deflects. The springs shorten, representing the soil settlements, and the spring reactions represent the soil's pressures. On the other hand, geotechnical engineers model the soil as a continuum, either as an elastic half space or an inelastic half space, to determine the corresponding soil settlements and stresses due to the column load. Now, here we determine what these soil springs are, especially under a raft. The K value, as we refer to it, which is also known as the Winkler spring or the modulus of subgrade reaction, is the ratio of soil pressures over displacements. So the units are units of pressure or stress over length. Now, the foundation response, there are significant differences in the response between the Winkler and continuum models. And this can be demonstrated easily by examining two extreme situations, a rigid foundation and a flexible foundation. And we will see that the contact pressures and settlements between these extreme situations, they don't agree between the structural model and the geotechnical model. I'd like to note that even a 4-meter thick raft can be flexible depending on the loads from the superstructure and the dimensions of the raft. Also, we are going to see in a second that a single set of Winkler springs, as we saw, cannot capture the soil pressures under a rigid foundation, or it cannot capture the soil settlements under a flexible foundation. That is for a single set of Winkler springs. for the case of the rigid raft, at the left-hand side, we have the structural approach with Winkler springs model, and it's a single set of Winkler springs, which results in uniform settlements and the uniform stress distribution. However, elasticity theory shows us that under a rigid raft, the settlements may be constant, but the distributions, the stress distribution is not, with high stresses developing at the edges of the raft. And the more rigid the raft, the higher these stresses at the edges become. Again, the rigid raft assumption depends on the size of the raft and the superstructure load. Now, by definition of the springs at the edges of the raft will have to be higher than the springs at the center of the raft to capture this stress behavior, where you have higher stresses but the same settlement. Now, in the extreme case of a flexible raft, again on the left-hand side you have a case of a single set of springs, which gives you uniform settlements and a uniform stress distribution. However, elasticity theory shows that the stress distribution under the raft is going to be constant, as opposed to what we had in the previous case, but now the settlements are going to vary, with the highest settlements occurring at the center of the raft and the smallest settlements occurring at the edges. Again, based on the definition of the Winkler springs, you would expect higher springs at the edges and lower springs at the center. So what is the solution for this? The solution is that we should not be using two zones of springs, but, the solution should be that we should not use one zone of springs, but at least two zones, with the outermost springs being higher than the springs in the center. Now, for a stiff soil, let's say, the outer springs may increase 30 to 40% compared to the springs at the center, whereas if the soil is soft, then we may need to increase the springs 2 to 3 times compared to the springs in the center. Now, again, the stiff soil and soft soil is relative to the foundation stiffness and the loading, and even rock would need to use two zones of springs, even if some may consider it that is stiff soil. Now, there are different methods to determine the K value, also known as the modulus of subgrade reaction. Method A consists of doing plate load tests. These values for different soils are available in your standard textbook, and they are not appropriate for the raft design because they only apply to areas that are 1 foot by 1 foot square. Method B consists of taking these same values and scaling them up in a crude kind of way. The more appropriate method is method C, where you would model the loaded foundation, probably with finite elements. Now, for method C, how you would do that, the geotechnical engineer would estimate the settlements and the bearing pressures at many points within the raft, and then it would determine many K values based on the pressure over settlement results, and they would draw contours of the K values and determine accordingly what kind of zones to assign and what kind of K values to assign to those zones. Now, if we're talking for the case of a Pile-Raft, then typically you would use also pile springs, which you would determine as pile force over pile settlement at each pile location. And these results you would then provide to the structural engineer. Now, we're going to talk about these concepts in a little more detail with a case study of a tower in Kuala Lumpur, Malaysia. Typically, we would start with a geotechnical investigation consisting of geotechnical borings, in situ testing, such as SPT or pressure meter tests, laboratory tests to define index properties, triaxial tests, one-dimensional consolidation, and geophysical methods to characterize the mass of the soil or the rock. Then we would use the results to determine the critical parameters and focus on those parameters in our model. These parameters would be the raft thickness, the location and the geometry of piles, meaning how many piles you would use, where you would put them, what kind of diameter you would use, what kind of pile. You would need to determine the soil modulus of deformation, which is one of the most critical parameters in the whole process. Then you would determine the method of construction, especially if you are dealing with piles. And you would determine the pile-soil interface strength. Then we would perform some hand calculations at the beginning based on elastic solutions to get a first-order estimate of the anticipated settlements. These typically don't vary more than 20 to 30% from the detailed finite element analysis. On the left, we see the typical 2/3, 1/3 method, where the tower load is transferred below the raft at a depth equal to 2/3 the pile length. On the right-hand side, you would see a classical Baker method, where the foundation acts as a block, and the tower load is reduced by friction before it reaches the pile tips. Typical input using the finite element method consists of defining the geometry, the raft, the piles, the stratigraphy, the material properties, the element selection, if you would use volume elements, area elements like plates, or line elements like beams, the boundary conditions, and the loading, which typically you could consider it a boundary condition. And with the loading, we mean the self-weight of the soil, the tower loads, and you would consider also construction staging during the construction of the foundation, maybe to model an excavation. Now this is a snapshot of the finite element model used to describe the various soil layers. Here we have a sand layer, a silt layer over a limestone layer. Foundation and pile geometry, this would be the raft. These lines here would be the piles under the raft. This here would be the extent of the excavation of the project. And at the top of the raft, you would put the loads coming from the tower. The tower is typically modeled by the structural engineer, and that is why you only see the foundation here. The tower stiffness and weight is captured as loads at the column locations. Now, here you see that this model is 200 by 200 by 170 meters. The raft is about 40 by 60 by 4 meters thick, and the piles here are 2 meters in diameter and have a length of 75 meters. Now typically the model would extend horizontally 3 to 4 times at least the length of the raft, and it would extend vertically 2 to 3 times the length of the piles, or if you don't have any piles, at least 4 times the length of the raft. Also note how the finite elements can capture the complex stratigraphy, which cannot be captured by simple hand calculations. Typical soil or rock constitutive models available with the finite element method is the elastic model, where you would need typically 3 parameters: the soil of deformation for the modulus of deformation for the soil, E, the Poisson's ratio, and the unit weight. And if you go to more advanced models, the more Coulomb is also typically used, where you also need to describe the friction angle and cohesion of the soil. More advanced models, such as the modified Coulomb, soil hardening, soft soil model or modified camp clay would require many more parameters, and you would need an extensive laboratory test program and check if your soil actually behaves like these models. For rock, you have similar models, elastic, more Coulomb, and a model that is typically used is the Hook-Brown, which is kind of reduced to a more Coulomb later on. Now, for the structures of the geotechnical model, let's say, we would model the raft either with volume elements or with plate elements. And we would describe either the modulus of elasticity, Poisson's ratio and unit weight for the volume elements, or unit weight and thickness for the plate elements. The piles, we have more options how to describe them, either with volume elements with or without interface, beam elements, again with or without interface, and embedded beam elements with interface. I'm going to go a little more in detail with the piles. The most accurate representation of a pile is with solid elements and interface elements, as it depicted on the upper left-hand side. This is the best model, but it may become too big for the computer to handle, especially if you have more than 30 or 40 piles to model. Now, for this exact reason, an element was developed. Here is described as line to solid interface model. It's also encountered in the literature as the embedded pile element, where you would model the pile as a beam. You would also model the soil pile interface, but you do not have to worry about the nodal connectivity. That greatly reduces the number of nodes and elements in the model, and is sufficiently accurate and can handle a large number of piles. An intermediate situation would be where you would model the beams with an interface. You would model the piles as beams with interface, but you would have to worry about nodal connectivity, which would also cause some problems for large models. Typical loading conditions, you would model the self-weight of the soil and the foundation, the raft. You would model column wall loads as either point loads, like for example what we have done here for this raft, or line loads or pressure loads to simulate the loads coming from the tower. And you would also again simulate the construction stages for the foundation. Especially if you have an excavation, you would need to take into account all the weight of the soil that's being removed. Some of the results in our example, here we see settlement contours for the raft, and these contours are typical of a flexible foundation where you have highest settlements at the center and smaller settlements at the edges. And even though this looks like a flexible foundation, it's a 4-meter thick raft, keep in mind. At the center we expect about 100 millimeter settlement, and at the extreme edge about 35 millimeters. Now this is a cross-section with soil settlements, again one of the benefits of working with finite elements. This distribution is typical of a Pile-Raft foundation where the soil settlements are relatively high at great depths because a bigger soil mass is engaged compared to just having a raft without piles. This is a soil stress contour plot under the raft, and it's one of the outputs that we use to help determine the K values or modulus of subgrade reaction. Again, we see some concentration of stresses at the edges. Here this is caused most likely because of the columns that are above that area in the raft. The cross-section, this is a cross-section plot that shows vertical strains, and it's typical of a block behavior where all the piles are closely spaced together and the whole foundation acts as a block. The loads are transferred below the pile tips, and you can see that below the pile tips you have this concentration of strains. A 3D plot of pile settlements with depth. We can see that at the top they follow the settlements of the raft, and we can see how they attenuate with depth. This again is one of the outputs we will be using to determine the pile springs at all the different pile locations. Similarly, this is a 3D plot that shows the pile axial loads, and we can see that these piles at the edge receive a higher load than the rest of the piles, mostly because you have some columns that are situated right above them. This is one of the outputs that you would use also to determine the pile springs. Now this is kind of an advanced plot where you have modeled the interface of the pile and the soil, and you can see it's a pile soil relative slip displacement, how the pile slips relative to the soil. It's of interest that because the group acts as a block, the slip starts from the bottom as opposed to starting from the top in the case of piles that act individually by themselves. So once you have gotten all your output and you have checked 100 times that it's correct, you determine the pile springs as reactions over settlements. You determine your area springs as pressure over settlements. And then you determine how much load is taken by the piles and how much load is taken by the soil under the raft. And then you provide the above to the structural engineer. Again, this is some of the results you get. Pile loads on the left to determine pile springs, and raft settlements on the right to help determine area springs. And this is something you would give to the structural engineer. On the left-hand side, we see the pile springs, with some of the springs at the edges being almost twice as high as some of the springs at the center. And you would also provide area springs. You would not give one single value of area springs, but you would divide it in different areas. And here we can see that the value of the area springs at the center is almost twice, or even is almost half or even a third of value at the edges. So the structural engineer takes the springs and runs their model again. And then they determine the settlements of the raft, subgrade stresses, pile loads, the Pile-Raft load sharing, and they check if there is any change in the wall loads. Now, we compare between the structural and the geotechnical engineer all these parameters, and if needed, we rerun the foundation model, or we just adjust the area and pile springs appropriately. Once we do that, we provide the new springs to the structural engineer, and this process continues until we converge. This is an example from a different job. We're mixing and matching because of confidentiality issues. And it's a project where we needed several iterations to get to final convergence. The plots indicate the differences of the structural and geotechnical model in pile loads, the top plot, and in settlements. So after an iteration, we see that pile loads and settlements, there are certain piles where the differences are greater than 20%, and we want to improve on that. After the second iteration, you can see that some of the changes may even change sign, and you have a reduction in the settlement differences, pile loads still haven't changed much. And you see that there is a change in the wall load that was greater than 10%. At certain locations, we will see was even greater than that. Another iteration, and then we start converging. Before we were we were greater than 10%. Now we're less than 10% in loads and settlements. Another iteration, you start converging in the wall loads, but still we needed to improve a little bit on the springs to converge more closely for pile loads and settlements. And for that project in particular, we converge of about 5% within pile loads and settlements, and the wall loads were all less than 10% difference between the last step and the previous step. This is a chart where we can see the shear-wall load changes during this iteration process. These are loads that are provided by the structural engineer, and we can see at the raft center how at the beginning we had some high loads, and at the beginning, at the edges, we had some smaller loads. Now, once you start doing this iterative process, you can see that load starts walking from the center towards the edge, and you end up with having of about 20 to 30% differences on the loads from what you started to where you end up, at the center and at the edges. Notice here how much the loads at the walls at the edges increased, which caused stresses in the walls. So some final remarks. The iterative process gives insight on the redistribution of column and wall loads. Now this redistribution is more pronounced when the superstructure is stiff compared to the foundation. And the redistribution may necessitate stiffening of the foundation. So if you see that this redistribution is causing too much stresses on the walls, you may want to stiffen the foundation, and to do that, you may choose to add more piles and or taking the piles to a deeper stratum or elongating them. That is the end of our presentation. Thank you very much.
Okay, so thank you, Kostas, for that presentation. Thank you, everyone, for attending this webinar. Once again, if you have any questions at all for us, and if you'd like to learn more about SOILWORKS, feel free to give me a call or to send me an email. Thanks again for your time, and we'll be in touch.